So I mentioned in a previous video that inductors behave half like capacitors, half like resistors. And we were introduced to the idea that inductors resist or oppose a change in current. Well, here we're going to talk about the energy storage half of it, sort of like capacitors are used to store energy. And capacitors, you simply charge and then discharge. Here, when we talk about an inductor, we still once again need a change in current versus a steady current. So energy flows into an inductor only when the current is increasing and is only released when the current is decreased. Alright, so our next goal is to be able to actually calculate how much energy is stored in the inductor. Once you've changed the current, gotten the energy in there, and then you have the current be steady, what energy is in there? Now, because the current is changing with time, and our goal here is to get to potential energy, because potential energy is stored energy, we actually have to go through power to get there because of that dt at the bottom of our relationship for the induced EMF. So we're starting with the idea that power is equal to VAB times the current, and notice I'm using a little I because it's going to change with time. And we learned in the previous section, essentially what we're doing is dropping the minus sign when we do VAB. Alright, so we also know that power is equal to the change in energy with respect to time. So I'm going to equate those two. And I want to pause here to reflect on the idea that you have this change in current in order to get a change in energy with respect to time. So that reflects what I set up here in this statement. Alright, I'm now going to cancel out the dt's so that we get the change in energy is equal to the inductance times the current times the change in current. Alright, so now I'm going to integrate from 0 to I, and this essentially is equal to work. The change in energy is equal to work. And so when I integrate this, I get 1/2 inductance current squared evaluated. You end up with 1/2 L I squared, or the idea, remember work equals the change in potential energy, so our potential energy is equal to 1/2 times the inductance times the current squared. Remember, we switch back the capital I because when you're actually figuring out how much is stored, the current then needs to be steady. So when we talked about capacitors, we talked about the idea that the energy is stored in an electric field between the plates. Well, here for inductors, we talk about the energy being stored in the magnetic field between the plates. So we say that the energy is stored in the magnetic field within the coils. So we have our magnetic field energy density. So this is energy density. So it's going to be in joules per meter cubed, and that's going to equal the magnetic field strength. Remember, the magnetic field strength depends upon the shape of the coil, so whether it's actually a coil or not, or whether it's a solenoid, divided by 2 times the magnetic constant. And technically speaking, just like we did with dielectrics, you can have some sort of magnetic material times the magnetic constant for vacuum. Though we don't very often introduce that concept because adding magnets to any problem just makes things super complicated.